Now remember that if this morphism T is the identity and Y is the kernel of gamma, then we actually now have a morphism, the connecting morphism that we desired, going from the kernel of gamma to the co-kernel of alpha. But how do we get this delta from a point of view of generalized elements? So we're going to be establishing, see delta T from here. Delta is going to be representative of some kind of natural transformation between Hom functors. And generalized elements, well, what are they? Let's think about that for a minute. If we have an object A and we have maps into it, I'll say like X and Y are maps into it. We're going to be thinking of maps into the object A instead of elements of the object A. So maps into, so X and Y are examples of such things. Okay. And when are they going to be the same? We have an equivalence relation, which is simply if we can extend back a diagram like this in such a way that we have an epi and an epi. That's the equivalence relation, and the equivalence class of X is what you call it a generalized element of A. Now, you can check that such a definition for a relation is an equivalence relation. It's obviously symmetric the way it's defined, and it's reflexive because you can think, well, you can use X as W itself if you're just working with X, and then you have the identity map, or morphism, which is an epi. So that works there. And then transitivity, you can also think by pulling back and then using that pullbacks preserve epis to get the epis that you need here. And also the fact that an epi of an epi is an epi. So you can use things like that. But anyways, we have an equivalence relation. All right, so taking a look at what we're going to do. All right, suppose we have, we're going to establish a natural transformation between the Hom functor of morphisms into the kernel of gamma, so generalized elements here. But I'm not thinking about the equivalence classes right now, just morphisms into kernel of gamma, into the Hom functor that talks about morphisms into the co-kernel of alpha. So we're going to establish a natural transformation, and this natural transformation will give a couple things. One, it'll actually give a nice set map between generalized elements of kernel of gamma to co-kernel of alpha, but it also, this natural transformation, just gives this, well, the morphism we've already found, but nonetheless, if you have a natural transformation, then by Yoneda's lemma in such a way, then this actually means that we have established a morphism from the kernel of gamma to the co-kernel of alpha, because by Yoneda's lemma, this set of natural transformations that we're looking at is just simply H of the co-kernel of alpha with the kernel of gamma plugged in, which is just morphisms from the kernel of gamma to the co-kernel of alpha, and we'll have, this is a natural transformation, so it'll be one of them. So it'll establish that fact. So to show that we have such a natural transformation, we got to check commutativity of a diagram here, and so we'll be working with that. Okay, so homomorphism or morphisms from Y to the kernel of gamma. We're going to take some element T in there. So kind of this diagram right here, T, and then this T of sigma and the sigma. We're kind of working with that in this way, kind of thinking about this diagram with Homs, where we're taking the H kernel gamma of sigma, okay, this way, which is just composition, pre-composition. And to check for naturality, you can look at this diagram, but essentially what we're doing is we're trying to show that these two morphisms are the same. So going back maybe intuitively, what does that mean? That means that if we go this way, okay, so we've used our methodology that we just ran through to find a morphism that goes from x to the co-kernel of alpha. That'll give us the exact same map as if we did it from y and then precompose that with sigma. So that's kind of the idea intuitively. Now how is this going to help us with generalized elements? Kind of thinking about that way. Well, if sigma even represents, imagine it represents an epi from an object x. You've pulled things back. So imagine you have something else that's also been pulled back to x. So if this diagram if this commutes right here, like pulling back sigma, like we were just talking along sigma, and we have the morphism that we get from here, and this commutes. So this is as we want, which is part of the natural transformation idea. Then that's saying that the universal element. Oh, so that means we're taking a whole class of T, right? So this morphism and this morphism right here, okay? So this morphism is the exact, this is a generalized, so the generalized, x to the co-kernel of alpha is a generalized element if you take its class, right, over the co-kernel of alpha, and similarly for y. And notice that they'll actually be in the exact same equivalence class. And so anything from y, right, from t over the kernel of gamma is going to be sent to the exact same thing. One equivalence class is going to be sent to the other equivalence class. Okay, so now let's take a look at the how we're going to do this, how we're going to establish this. So one step at a time, but it won't be too terribly bad. So thinking about what's going on here, we pull back. So the first thing we did was kind of pull things back here with a little diagram, one or the other. And because of commutativity of how things are working here, as we go with this map and kind of this map and this map and commutativity right here, we end up establishing a unique map between the different pullbacks with commutativity happening. All right, so we get that. We get this map, call it eta or something like that. All right, then we also, from this, kind of seeing how these go, right, because we have this commutativity here and even here, right here, because of this commutativity in this spot, then we have this map going down to that. Hey, those downward maps kind of actually give us commutativity on these maps that we have over here. All right, and you can kind of, and we can kind of look at that because we have, and part of that is actually due to this morphism right here being a mono. And I wrote out a few details here that you can look at. But essentially we get commutativity there with an equalization to get it. Okay, and then we're over here, universal property of kernels. You can think about the kernels of these maps coming back. And since you have commutativity over here, you have commutativity there. Great. So we get some. Now let's get to the meat of this. All right. So, okay. So we can draw a diagram kind of focusing on the part that we want here. And the idea is that we want to establish that running this way is the same as this way. We'll do this in pieces. So this map right here is the same as this map. That was part in the definition of how this came about. But we also, our different commutativities that we're showing in the diagram are actually positioned here. And we can see them at work. So we can move down here, and then we can move there, we can move there, and oh my goodness, by uniqueness of this, so coming from here, okay, from this map right here, going to, there's a unique map from X to this co-kernel of alpha using the universal property that we were using of this X being the co-kernel of this map right here. Okay, the uniqueness of that, this direction and this direction will be the same. So by uniqueness, we get it. We get the commutativity that we were after, and all the other ideas we were mentioning fall into place. Thanks for watching.